Moving on to section 4.3, we're going to look at Riemann sums and definite integrals. So our three objectives are to understand exactly what a Riemann sum is, and then to evaluate a definite integral using limits and geometric formulas, and then to evaluate a definite integral using properties of definite integrals. So before we talk about a Riemann sum, I want to sort of remind us where we just were in section 4.2. And in section 4.2, what we did is we had a function like the one shown here, and we would divide it into equal intervals, and those equal intervals would then give us either the left-hand side or the right-hand side. And we're going to do the exact same thing here, except if you'll notice, we don't have equal intervals on the x. So instead of taking whatever b minus a divided by n was, because that would be the equal intervals on the x-axis, now they're saying those x values are found by taking I squared divided by n squared. But we're still using delta xi the same as we did before. So just as we did when we had equal intervals, I want to find the width of any old interval. So if I find the width of the ith interval, essentially saying some interval, I need to find the width of it. And that is found because remember on our last page they told me c sub I is found by taking I squared over n squared, and c is just really the width, or the position, the position on the x-axis. And just as a reminder again, because I'm going to use it in a little bit, my function was x, the square root of x. Well, the first thing I want to do is find delta x, and so I want to find some position minus the position before it. Just like before I always did b minus a, this is exactly what I'm doing, is I'm not taking b minus a, the endpoints, I'm taking the endpoints of an interval. So I'm taking c of I minus c of I minus 1, which is c of I and c of I minus 1, and subtracting them to find the distance between them, which turns out to be 2i minus 1 over n squared. So that's delta x, and notice this is the same function I used before, and now delta x is going to be this guy. Now what I'm going to do is I'm going to take f of ci. So f of ci would be the square root of I squared over n squared, which of course then I'm going to continue to just reduce as much as I can. So the square root of I squared is I, square root of n squared is n. I'm distributing this. I'm taking that 1 over n cubed to the outside, leaving me with this. I'm basically going to find the summation of each of those separately. So I took 2 to the outside of this, and then I squared. This is that function that we use for I squared. And then minus, and then I, so this is that function that we use for I. Notice by doing that, I can get rid of the summation. And then from here, as I always say, it's just algebra. So I skipped a lot of steps in between that I would want you to show, but essentially what I'm doing is simplifying all of this stuff and all of this stuff and all of this stuff until I get something that's a little bit easier to deal with. And then I'm going to essentially make them 3 separate things so that I can then find the limit of each of those as they approach infinity. So 4n cubed over 6n cubed gives me 2/3. 3n squared over 6n cubed gives me 1 over 2n, and then n minus n over 6n cubed gives me minus 1 over 6n. From here, I'm just finding limits. So the limit of 2/3 as we approach infinity is 2/3. This guy turns to 0, this guy turns to 0. My answer is 2/3. So if you'll notice, even though I kind of threw in a curve and said, hey, we don't have equal intervals anymore, everything else is exactly the same as what we did in 4.2. And the reason that that was okay is that as n increased, the width of the largest subinterval, which we call the norm, approaches 0. So it's essentially the same thing we did before. So you might see this, which is the 2, like a 2 absolute value sign with the delta in the middle. That means norm. And essentially what we're saying is the norm is delta x, which is similar to that b minus a over n that we used when we had all equal intervals. It's all really the same thing. They're all equal. So for a general partition, the norm is related to the number of subintervals. So we can say b minus a over the norm instead of b minus a over n. And we know that's going to be less than or equal to n. So this is going to be important as we look at definite integrals. So let's take a look at Riemann sum, the definition, which is going to sort of put together things that we've already talked about. We have a function that is being defined on the closed interval from a to b. And essentially what we're saying here is a is my left-hand side, and then as I move to the right, this is not the width of the interval, but the position of the interval. So basically I'm listing my x values of my interval from least to greatest, so in order, and then my right-hand side would be whatever b is. So before, when we started at 0, and then we said it was 2/5, and then it was 4/5, then it was 6/5, you get the idea, all the way up to where we ended up, which was 2, those would be my positions on the x-axis. So those would be equal partitions, obviously. These are unequal. Delta xi is going to be the width of the interval. And if ci is any point, so ci, remember, is one of these positions, any point on the subinterval, then the sum delta xi times the function of f of c of I is going to be called the Riemann sum for the partition. So what does all of that mean? Exactly what we just did. So I showed it to you before I told you what it was called. Essentially, we're finding the sum of the function using some random arbitrary point ci in our function and delta x, and that's going to be our Riemann sum. So the number of subintervals in a partition is going to approach infinity, which is what we wanted. Just like before, we found it for 5 rectangles, and then 10, and then 100, then 1,000, then 10,000, and then we actually found the limit. And that's what we're going to do again. We're going to approach 0 to find the limit, which means as the norm approaches 0, n approaches infinity. So we're still just finding the limit as n approaches infinity.